So my name is Melanie Warrick, and this is Andy Petrella, and we are here to talk to you guys about deep learning and NLP with Spark. And specifically, if you don't know, NLP is natural language processing. So we're going to show you a demo, and I'm going to give you just kind of an overview of a few things before we get to the demo. First off, how many of you have done machine learning? All right, great. We got a lot of people in the crowd that have done machine learning. That's fantastic. Well, for those of you who haven't, I'm just going to do a real brief overview. Machine learning, the way I like to explain it is that it is about pattern recognition and prediction and using algorithms to do this. There's a number of different types of algorithms that are out there. The one in particular that we're going to go through today is known as natural language, or is known as neural nets, using natural language processing. Now, when we talk about machine learning, just to give a little bit more information, some great examples that exist out there, and this is actually a really great example that exists out there. DeepMind, which is a company that's owned by Google, recently won against the world champion in Go. They were able to create a program called AlphaGo, and it beat the world champion 4 out of 5 games. That world champion, Lee Sedol, was surprised. What was the most interesting thing about this is that there was moves that DeepMind's game would play that a human would normally write off as being a bad direction to go in. But the AlphaGo system was able to assess a larger search space than what Lee Sedol was able to take in and understand that it could take hits, it could take losses that you and I would think would be a really big mistake or even a small mistake. And it knew that those hits would actually not derail it and if anything, give it the opportunity to win bigger later on. So machine learning, it's taking algorithms, it's making the ability to adapt and to learn, to allow that program to adapt and learn. Another example that I like to share is in Switzerland for search and rescue. They are using drones that have been trained on images of different hiking paths, and those drones have actually been shown to be able to identify anomalies in those paths to help track down people who are lost. They're identifying those anomalies about 3% better than humans so far. And another interesting example, most people will write off speech recognition right now because when we talk about speech recognition devices, when we look at Siri or some of the other examples that are out there, we're like, well, we can't have a conversation with it, so we write it off, right? Because I've watched Star Trek. I expect to be able to have a conversation with my computer. I don't understand why it's not at that point yet. But the reality is, it may not be at that point yet, but we are getting so much closer. We are so much farther along than we were even just a couple of years ago. And we didn't have some of these devices even when we got into the 2000s to begin with. Viv was just recently announced by the team that created Siri. And Viv is this next step in what is known as natural language processing and speech recognition. And if you haven't checked it out, I'd recommend it. You can't have necessarily a coherent conversation with Viv yet. However, you can ask Viv questions that are much more complex than you've ever seen before, like show me the countries that were above 40 degrees Celsius on Thursday. Or show me the cities that were above the 40 degrees Celsius. And supposedly Viv is able to go in and give you that kind of nuance and that kind of detail. And language is hard. It's hard enough with one language. And we have, so many different languages throughout the world and different meanings in the way that words are put together and the tone of the way the words sound. So language is hard. This is definitely a hard problem. And when you get into natural language processing, there's a number of ways you can approach how you're going to apply it. Regularly, you'll see chatbots, or you'll see, and I know some of the folks in speech recognition don't like the term chatbot, but you'll see question and answering types of solution. You may see something where you're getting image captioning, where you'll have some type of image and you're trying to identify objects in it. Or topic modeling is very common, especially if you're working with any kind of recommender engines. You're trying to identify sort of core groupings, core topics that will go across ranges. Language machine translation, language translation in particular, I know we've seen some great examples. I think Skype's got this incorporated where you can speak in one language and have it pretty quickly translated into another, like speak in German and have it translated to Chinese. And then language generation, there's some fun examples out there now where literally you've got bots that can, generate something that's almost akin to Shakespeare after it's consumed all the Shakespearean text. But what's more interesting is the commercial applications. We are already seeing that they have bots that can generate articles, news articles. Now, before I get to the example, a couple other things I want to give you an idea about. As I mentioned, this is about using machine learning and specifically natural language, or I keep talking about natural language processing, which is what we're doing, but specifically neural nets. Now, neural nets, it's a very complex topic. It takes a lot of time to explain, and there's some great resources out there to delve into this in more detail. But if you have not experienced or looked at neural nets in the past, I'm going to try to give you a little bit of an understanding. If you've seen it before, then this is going to be pretty basic. You have a model that you're trying to generate. It's almost like if you're doing linear regression. Linear regression has a model. That model's pretty basic. It's y equals mx plus b. When you are fitting your model to whatever problem you're solving, you're going to be tweaking that m and that b, your coefficients. Now, this is a model that you're trying to fit. This is a much more complex model. It operates in a much higher level of dimension than 2 dimensions, like you would do with linear regression. Now, this model uses linear regression. It uses some level of linear transformation as well as non-linear transformation. If you don't know what that means, spend some time doing research, but just understand there's some changes that it's doing to the data. And ultimately, it's taking whatever data you're feeding it and question you're trying to answer and trying to make this adapt to that question. What's happening is usually you're bringing in an input. You break down that input for it to consume. And every node that I have up here that's blue is representing a different node that would be doing some type of computation. And it's doing its own fitting to the data. So it's not going to look the same in terms of the way it fits between every single blue node. They're all going to be unique in the way they look at the data that it's ingesting. And when it gets to the end, it's going to see what is my loss. Now, usually when you use neural nets, or more traditionally when we've been using neural nets in commercial applications, we've been using it for supervised learning, which means it's labeled data. So we know what the answer should look like, and we can get an error, and then what we do is we literally go back into the net, and we're going to update every single node based on how much we think we need to change it to better fit whatever we're solving. Yeah, it's abstract, it's a little kind of nuancy. Like I said, there's a lot more detail to this, but just understand you're taking in some data, you're doing computations on that data, and you're doing it in multiple places with different variations on that computation. You get to the end, you find out what the problem is, what the error is, and you're going to go back and try to adjust this model. You're doing tweaks. And you just keep doing that until you get to a point where you have a good score. So that's a neural net, roughly. Now, these blue nodes, this is a very simplistic model. Now, technically, you can just have one blue node, one computation node, and you've got a neural net. But really, you're going to usually have potentially hundreds, thousands of nodes, depending on the problem you're working with. And each problem is kind of different in how you tackle it. And this is also a very basic, simplistic structure. There's some pretty well-known established structures for certain types of problems. And this one would be known as your sort of feed-forward, fully connected structure. It's very simplistic. Everything's connected to everything else. Now, the structure we're going to show you guys today, or the structure that is used in the example today, is known as recurrent neural nets. Now, the difference with this structure versus what I've just shown you is that this structure is allowing you to keep track of state. What it does is it allows the model, each of those blue nodes, to know what it saw before. And it is in that way able to say, I understand what I saw just recently, and I can make some better decisions because I have a sense of what came before. This is very crucial when you're working with anything that's time series related. And when you work with natural language processing, you're working with orders of words. The order of the words actually matters, and that's something that you want to take into account when you're working and trying to assess it. Now, recurrent nets, this idea has been around for a really long time in this space. I mean, actually, neural nets, frankly, have been around since the 50s. And the recurrent net algorithm has been around, or this structure has been around for a little while as well. The thing is, it was not seen as being very useful or valuable for the longest time because there's some issues with vanishing and exploding gradients. If you don't know what a gradient is, Just understand the gradient is what you use to take the error and go back and make changes to your net. But ultimately, it's got issues with what's happening is that the computer is having a hard time keeping track of either the values get way too small or way too large. So it's going to 0 or going to infinity, and you're basically unable to go back and take errors and propagate them back into the net. So this was one problem that Recurrent Nets had. And along came long short-term memory, the LSTMs. This is a variant on recurrent nets in particular. So whenever you hear about recurrent nets being used, understand that the LSTM is what is usually being used to solve the problem. There's so much more to this. Again, I highly recommend spending some time researching it. I just want you to have an understanding. We're going to use neural nets as our model. We're specifically using LSTMs to solve this problem. And that, this information will be useful to further investigate later down the line. Okay, a couple other things. So the great thing about using recurrent nets, or LSTMs, is that you can have different variations on your inputs and your outputs. Usually when you work with any other kind of models, you're going to have a standard one-to-one relationship, that one on the far, well, I guess to all of you guys, it's the far left. So the one-to-one is what you'll have. You'll have like an input of an image, and you'll have an output of a title, or a description of the image, or something like that, or an output of a word to the image, let's say. Now, a standard one-to-many situation would be something like a word Tyvek, where you are going to take a corpus of words and you do a relationship to those words. So you say, I have one word, and here's a list of all these words that are in close relation to that one word. And that's a well-known model that exists out there in terms of giving us some similarities between words. Another example of one-to-many that has been done in the last couple of years, and this, I saw this example actually being mentioned yesterday. It's called image captioning. There was a significant amount of research that came out from a number of the big players in the space. And what they were able to do is literally take images, and as you can see here, not only identify objects in them, but come up with descriptions, come up with actual sentences to describe what this image is showing you. So that is an example of your one-to-many. What we're going to show you today is taking several reviews, so that would be your many, to one, where we're going to try to show you, is it a good or a bad review? Do we want to go see this movie, or do we not want to go see this movie? Other examples that exist out there in terms of leveraging recurrent nets, especially in the NLP space, is you may be doing language translation like we talked about, where you would be doing something like German to French. Or you could be doing something where you have video, and each image in that video, you want to have some type of word associated to it. So those are just to give you a sense of the sequence to sequence, and when you're thinking about input and output for the neural net itself. So as I mentioned, we're going to do sentiment analysis, and specifically we have a number of reviews. We're going to put those into the net. We're going to have it come back and tell us good, bad, not so good, really just good, bad. Okay, and what we're going to use, or what we are using in this example, is a couple things. From the reason why I'm here is because I work with Skymind, and I'm an engineer with Skymind, and we produce, or we develop Deep Learning 4J, or DL4J. It's Java-based solution in the neural net space that integrates very easily with Scala. If you've heard of, I don't mind saying it because I work heavily in this space, if you've heard of TensorFlow or Caffe or Torch, we are also a library, but our difference is that we are based in Java, and we are able to integrate with Scala, and we also integrate with Spark. We use Canova, that's another one of the platforms we build out, as a way for you to convert any kind of data that you're trying to pull into the nets. And we're built off of ND4J, and that's really our version of NumPy, if you've worked with Python at all. But ultimately, it's a linear algebra library, and we've recently integrated it where we have it pretty much based off of C. So all of these neural net libraries are leveraging C to optimize how you're working within memory. So ND4J is built off of libND4J. You really don't need to know about libND4J. We handle all of that for you on the back end, but I'm just making you aware. So ND4J, Canova both support DL4J, and DL4J is where you're going to build out your models. And that's the information about Skymind. And the other thing to note about us is that we've been building this out. It's open source. We're always looking for people to contribute, so happy to have people help out, especially with some of the work around Scala bindings. But our goal is working to integrate so we can provide this for enterprise solutions. And from there, I'm going to hand it off to Andy. He's going to talk to you about the notebook that he's building the notebook that his company has provided, and it's going to be part of this demo.
Thank you. Actually, yeah. Hello, everyone. So, thanks, Melanie, for this great introduction to NLP. Before that, just a few words about the Spine Notebook. I don't know if some of you were at the talk that I gave yesterday with Dean. No one? A few of you? OK. I present at the end of the talk the repo that we use in order to present Scala as the data science language, and also a few notebooks that explain what kind of library you can use in Scala to do machine learning. And it includes, of course, the L4J with MLlib and other things. But necessarily for deep learning, you have to go to deep learning 4J. It's the best that I've used so far on the JVM. So the Spine Notebook is simply a web page that I will show an example to run some NLP. De La Felas is the company that I've created a year ago with Xavier, where we do data science on data science. That means that we are doing recommendations for data scientists based on the information that we can grab into the system where the data scientist is working on. Essentially, we are doing recommendation for the guy that does recommendation. We had a project actually with Skymind a few months ago. Skymind, Canonical, IBM, and NVIDIA. And for that, we created Juju, a Juju bundle. Who knows about Juju? Right. Juju is a very interesting tool. It allows you to create and package tools, link them together, and deploy the whole thing at once onto Ubuntu clusters, but they are supporting it to CoreOS and other platforms, including AWS. So it's very interesting if you want to build a whole cluster and deploy it at once using a simple command. It's not so far for Terraform, to be honest. So we share with them a Juju bundle that includes DL4J, so you don't have to take care of yourself about the dependencies of DL4J and so on. It installs Mesos, Spark, and the Spine Notebook as the client. So it looks like that, actually. So the Juju will allow you to install all these things in one single line onto your repo to do a WS or whatever. So this blog is explaining what has been done there. What we've done actually is to do some NLP analysis on logs in order to detect failing nodes on an OpenStack cluster. Well, so regarding the notebook that I want to show, so yeah, this is the Mesos cluster. I just wanted to show that we have done the work in order to have GPUs on Mesos. So we can schedule also GPUs on this Mesos cluster, so we can leverage that. Because of course the L4J, with libnd4j behind it, is also linking to CUDA, so you can leverage the GPU power for your analysis. Well, so I'm going to add a few things there to leave more room. Yeah. So can you see that? Maybe I should increase a little bit the font, something. There we are. Is that okay? So the idea here is to do two things mainly. So we want to do NLP, right? So we want to analyze texts. The texts that we are going to analyze are the IMDb recommendations, the reviews, sorry. So we have a lot of reviews in IMDb. I want to see if it's a positive review or it's a negative review, right? And what would be the purpose of that is that you can then check if the score assigned to a movie is actually respecting what are the comments in there, because there is a high chance that the comments are more important than the stars themselves, because the engagement is higher. So in order to do that, so we'll use a recurrent network, and specifically the LSTM to solve the error propagation problem. And to do so, first we'll convert text, the reviews, into a space which is computationally interesting, so we can do computation on it. And the space that we're going to use is the word Tyvek one, right? As Melanie has explained. In order to do that, so we will use something provided by Google. Google has trained a model and put it publicly available. They trained a Word2Vec model onto their Google News data sets. So there are a lot of words in there, and they have a lot of information. That means that the space is pretty well optimized. So this notebook will be provided very soon, so we're still working on it to clear a few things in there, but we will share it publicly with a repo and so on. Melanie, you can follow Melanie Knightley Hall on Twitter. She will provide all the details about it in a few times. Well, so this notebook, as usual, is including a lot of dependencies to show you what it looks like. So you can go to the edit notebook metadata. And there you will see that we have imported ND4J here, deep learning libraries, including some native stuffs in order to be able to access the underlying architecture. And also we have including a Spark binder. Well, and then the notebook will take care of downloading all the dependencies from internet and so on, so you don't have to care about it. So we have the dependencies, so we can just paste in a cell, execute it, and then they will be imported. Behind the scene, there is a REPL that takes care of the imports and that will track the evolution of the notebook. So each cell is actually a line which is sent to the server and executed. So the first thing that we'll do is that we download this file, right? And this file is 1.5 gig. So it's huge, right? And it's huge, and also it's going to be local. So of course, I'm not going to run the notebook now because it's going to take some time, so I have already prepared it. But the thing is that this information is very interesting because this will convert the data set that we're analyzing in the right space, and hence it's going to be very efficient at the end. Right, so we just download it. Then we can extract it, and at some point, we are loading it. So there is a very helpful loader in DL4J named Work Vector Serializer, and then you can load directly the binary, because actually Google is providing a binary which has a certain shape, and this loader takes care of the loading efficiently. So you just have to provide the path to it, and that's it. Okay, I skipped that because it was a previous try. So now that we have the Google model in memory, which takes 3.5 gigabytes in memory, right? Because it expanded, so you have so many words, and each word has 300 dimensions, right? So it's a 300-dimension space, where each word can be placed, right? So it's very, very large space, of course, right? That means that it's very important to have a lot of word in your corpus in order to fill the space correctly as well. Otherwise, you might have a point that will land somewhere where there is not much information, and then the resolution is, the accuracy will be might be poor at that time. Right. So you want to parameterize the model. So as Melanie says, it's going to be many-to-one. And to do that, so we'll try to do it into a let's say, batch manner. So we'll take batches, and then we'll train the algorithm on the batches and aggregate at the end. So the batches is 50. The vector size, as I said, is 300 because we have 300 dimensions for each word. The number of epoch for the batches is 5, and then we have something that allows us to plot. The functions that we are going to use, which will be softSign and softmax. Right. Now LSTM, which is the purpose of this talk at some point. How would you create such layers? So now we're talking about layer now, right? So you have this Graves LSTM, which is a variation of the LSTM builder layer. And you can provide the vector size, which is 300. So we take 300 words that have been converted into 200 space, and then we will change it into 200 units, which will be the number of time step, right? And from the time steps, so we'll learn how these steps are linked to each other using the recurrent network, and then we will output the answer, which will be either positive or negative. Of course, we have a trained data set. To do that, so we'll use the softmax for the activation, and the loss function is the max extent, which is actually an estimation of the distribution, which is very efficient to segregate where the data is. Now that we have built the layer, the output layer, using an RNN, then we can finally build the whole thing. So you can use the neural network configuration builder to do that, and we pass several things which will be important to the optimization phase. First, we will use SGD, right? So because we are doing batches, then we will use SGD in order to optimize our algorithm with only one operation. We will use the propagation using the RMS. The regularization is using a magic number using the L2. It's pretty usual. So we might have used the elastic net maybe as well there. I don't know. Maybe we might have used the elastic net as well maybe there because there are a lot of dimensions. Anyway, the way it is Xavier is just a good way to initialize the primary weight vector. And then finally we'll have, so I can skip that, but the running rate is one of the the hyperparameter. Again, it's a magic number that works pretty well. Yeah, all the magics there. Who said that machine learning is not magic? Some part is magic. Not really, actually. There are a lot of work that has been done before to find this number, of course. Then we create the layers, and then we put them into the model. So we have two layers there. One layer with one output layer. And then finally, we say that we want to propagate the error, of course, and then we call build in order to have the model. Then we have this fancy JSON representation of the multi-layer configuration that we can store if we like, reload, and so on. Now that we have the configuration, of course, we can build a network onto it. So we call the multi-layer network builder. We initialize it. We have the model that we can now start training. But the way we want to train it is using Spark, right? So we want to leverage the fact that the data can be distributed, okay? To do that, it's pretty easy, actually. You can just use the Spark DL4J multi-layer implementation, and you just pass to it some configuration regarding the way you're going to aggregate information in distributed manner. Of course, because all machine learning is done like that right now. So you distribute, you train locally on each partition, and then you aggregate in each, let's say, hyper step. So the aggregation is using average in this case, pretty common in this case. And finally, we initialize the Spark DL4J multi-layer passing the Spark context so you can access the data using the right configuration and the net. Well, this is now the data preparation, where we are getting the information for MDB. And the MDB data is organized in this folder. So we have a train and a test folder. And in this train and test folder, we have in each of them pos and neg folders, which contain a bunch of files, right? So for each review, we will have a file. It's a pretty bad way to create data set, but then we have 12,500 files with one review, single line generally. So that means that for distributed it's going to be tough, but there are solutions to aggregate everything and then distribute the data. So I'm explaining everything there. So you can go through the notebook when we distribute it, and then you can check all the mathematical reason and how to do it and so on and so forth. But the main idea is that at some point we take this information, which will be converted into 10 times 300 times 100. So we will have data set per batch, 10 reviews, right? Each word is converted into the 300 space. So each word is 300, so 10, 300. And then 100 is the number of words that we will keep in each review, right? Number of words that we will keep that is also in the Word2Vec model, of course. Because the Word2Vec is a gigantic map assigning a word to a space, that means that we will take only the words which were already present into the Google News data set that Google used for their stuff. And at the end, for each data set which is packing, each batch, we will return the value for each labels. Then you will have a 10 times 2 times 100 result. Sorry. To do that, easy. We have the feature. So we have this word to vec. We get the word vector matrix from the token, which is a word. And then we get the vector, which is the 300 thing, and we convert it into an array using the ND4J library. This is still using the ND4J, but I have to mention that there is also an ND4S layer on top of ND4J, which is the portage of the Java library to Scala, which is a more idiomatic Scala library, which is very cool because then you can leverage the architecture of your computation, your machine to do some linear algebra in Scala. Worth checking, to be honest. Okay, so then we will download this data set, we expand it, we load it. This is just showing the files actually, so it's pretty long. So we have 1 file per information per review, as I said. And this is the first review, so about this movie that honestly I don't know. Who knows this movie? Yeah, it's the 3rd time, no one. Yeah, maybe it doesn't exist. I didn't check, but maybe I should check. Anyway, actually, this woman who is a teacher said that she's very happy about this movie, which is apparently respecting how college is working or is working in the US. Maybe she created the movie. I don't know. Yeah, but then we have to go through these files and then we have to aggregate things and so on. So I will skip the details. This is done into the sentiment example iterator. And then there is something bad. I'm sorry about it, but we are working on that. So we are doing something on this iterator, which is iterating over the files and packing them into 10 examples. What we do at some point is that we go over the whole data set normally and we load it into an iterator, which is the buffer, and we serialize it. So there are 2 reasons why it's done like that. The first reason is that, having 1 file on the cluster, if you have HDFS, that means that you will have to reserve a block for each file. That means it's very bad. So you lose a lot of space on your disk for just 1 file. This is the first reason. But the most important reason is that if you want to convert your reviews, in a distributed manner, if you have the file distributed, that means that you have to have your walk-to-vec vector present in each machine in the cluster, right? But a walk-to-vec vector is 3.5 gigs in memory. And that means that it will take quite some memory on each executor. And for sure, now we are thinking about how to distribute it from the driver on the cluster using broadcast or something like that, but it might take some time, or squeezing a little bit the Spark API in order to allow this model to be loaded distributed manner. So this is something on which we are working on because this is a limitation, but there are many ways to work around it. So here, the way to do it, at least to have a bunch of information distributed, that we take a bunch of them and we distribute it using the ProRes mesh on the Spark context. Now we have the data set distributed into the walk-to-vec space. So how do we train the model right now? So in a distributed manner now. It's pretty easy. So we take the Spark network, we fit the data set onto the RDD. And that's it. It's pretty usual in machine learning is that the API generally is simple when we compare to the mathematical, theoretical, concept behind it. So generally the API is, okay, you configure, you pass the right hyperparameter, and you train, and it's done. But of course, we have to understand what's going on behind in order to, to interpret correctly what are the results and how to configure it correctly, by the way. So you fit the data set, and you get back what? A trained network, something that we can save on Parquet or whatever, like it's done in Spark already. And when it's saved in Parquet, you can load it in a stream or whatever. So in a stream, you can predict reviews using the predict method. Here, I'm just showing us a quick example. So we do the same thing like for the trained data. We take all the files, we arrange them into data set 10 by 10. We serialize it, and then we can use the predict function that will return the predictions, which will be essentially for each entry in the data set if it's a positive or negative. We can also have access to the scores if we want to check a little bit in more detail what went, what was the initial score onto which we had decided if it's a positive or a negative. As I said, so there are a few limitations and next steps. So this is on what we are working right now before distributing it. We have to distribute the data initially, parallelizing the projection onto the work2vec space. As I said, this is pretty hard. And so this is done actually now. The predict has a few problems. So this, oh man, this is now done. So wait a minute. Okay. So we are now able to do some prediction of very large data set like AMDB in a streaming manner and so on, and actually the code is pretty simple. Of course, there are a few limitations because we are working in distributed systems, but that means also that we have a lot of work as a data engineer and data scientist in order to have our environment ready for the challenges that we will have to face for the coming years. But I mean, yeah, we would be bored, of course, if everything were already done, right? By the way, this is the GitHub folder that I've mentioned initially. So this is Scala for data science, and there are a few things there that you might want to check. That mainly in this branch that I will merge soon. There are 3 notebooks. One is explaining why Scala for data science, why using the Spine notebook as a tool for data science, and what are the different libraries that you might want to check for doing data science, like DL4J, Smile. Smile, I recommend it, especially if you want to do some training or learn machine learning, because it has 98 models and algorithms implemented there, although they are local, and all the libraries that have integrated it there. And there is, by the way, a Docker for it. So this Docker is actually, so if you check the tags, it's prepared with Cassandra, Spark, Spine Notebook, and Spark 2.0. So it's already prepared for Spark 2.0, so you can already use it for these kind of things. I'm done with that. So there are a few references. I will leave it to you.
Right. So this last part here, this is some references that I've listed to give you guys one kind of a resource where you can go look for additional information on RNNs. Also, some of the repos that we've mentioned. And if you're taking photos, just to let you know, if you're on Twitter, at Night Owl is where this deck is currently posted. Image references. So I'm at Night Owl. Andy's at Newtsab. Am I saying it right? Newtsab. And that's pretty much what we wanted to share with you guys today. So thank you very much for listening, and we'll take questions if you have any. Yes.
There's one.
I actually have 3 questions, so you can pick one. So do you want the machine learning, the optimization, or the monitoring question?
So there is one question behind it. We have to pick one. Yes.
Which one?
Whichever one you want to ask, go for it.
Okay, so I take the monitoring one.
Yeah.
When I train models, I usually need some hours for one epoch of training, and so monitoring comes important. I want to see the learning curves, the training errors, the validation errors. Is that supported by your solution?
Yeah.
Yes, you can monitor and see how the score is improving or not improving, and there's some additional kind of monitoring tools. It's set iteration listeners is what you would do on the model, and there's some examples we have in the examples repo that I've got in that GitHub repo.
There is a score iteration
yeah.
listener as well.
Yeah, you basically will say when you create your network, then you'll say network.set iteration listener, and there's a couple listeners you can pass in. Like there's histograms in particular that'll show you that kind of information. Histograms that'll show you sort of how are you doing with your scores, how are you doing with the gradients.
Yep.
Okay. Any other questions?
If you want, I can.
You can ask your other question. Go for it.
Okay, let's take the machine learning one.
Yeah.
You mentioned that you were using elastic net for regularization.
No,
that sounds really weird because why would you use for sparsity on neural nets?
I mean,
right?
because there are a lot of variables you might want maybe to get rid of some, I don't know. Just thinking about it.
Yes.
Yeah.
You should definitely use dropout.
Yeah.
It works really well. Okay, do you want the third one?
So
It's the
actually,
hardest.
well, let me just say, because I know you were asking about sort of, in essence, you're talking around regularization. And something to note that I didn't get into too much with the model, but one of the challenges with neural nets is that they can be overfit easily, meaning that they're too perfectly associated to the training data, and they don't generalize. So if you send it something new, it's not going to give you very good results on that new item. So you use things like dropout and L2, which Andy had mentioned, to regularize, meaning give it still some level of the haziness, some level of it's not perfectly matched to the data that it saw so that it can better generalize to other problems. And then you had a third question?
Oh, you really want it? Because that's the hardest one.
Bring it.
So it has to do with the optimization. If I understood it right, you send the training data to all the nodes, and then you run mini-batch stochastic gradient descent on that node. That's not the best optimization algorithm, you probably know that, but the question I'm getting is...
Distributed, you mean?
Yeah, I mean the distributed. So I'm running it on single GPUs because I've made really bad experience with multi-GPUs. Our multi-GPU computer died, RIP, rest in peace. And distributed was always slower, so we have 10 nodes with one thick GPU. It was always really slow up to, I think, a few nodes. So I rather run 10 experiments concurrently on 10 single nodes than distributed. So, but if you send all the data to the nodes, you don't really have a distribution, right?
Wait.
So, okay, so you're talking about the optimization in terms of distributing it across multiple GPUs or multiple CPUs, and if you don't know, GPUs are a different type of chip that's used for parallel processing and to speed up the training process. So you're speaking specifically to a technique that's applied is distributing it across multiple GPUs, and the typical approach is that you will send the data to all of the GPUs, and you'll split out the data across different GPUs, and you'll have the model on all of the GPUs. There's a couple of different ways you can do this, but the model would go on every single one, and the data would just be split out. Depends on how much data you have and how large that data is that you would want to use and distribute across multiple GPUs. It has been shown to actually speed up performance. I know the larger guys out there like Google and Baidu and so forth are experimenting and using that type of solution. So sure, if you can feed your data all through one system, typically that's a more solid solution to go with to start out with. But if you find that you want to bring down the number of hours, days, months, whatever it is, because you have so much data that you're trying to process, that's when you start to explore splitting out across multiple systems and splitting the data out across multiple systems.
Yeah, and there are other problems with SGD in distributed. The partitions sometimes are skewed, or very often. That means that when you train the model, the model is very different on each machine because the data it holds is very different. That means that you might want to first shuffle the whole data before doing that, or you might check as well the splash library. And the splash library is doing bootstrapping on each machine. That means that it's a bit stressing the variability of the data set before aggregating locally. So there are a few techniques now, and what I said, we are in distributed environment now, so there are a lot of research going on. And this is one of the most important one regarding SGD, I would say.
Right, and actually I want to add something. Whether you do distribute it or not, it's pretty common nowadays with neural nets to batch the data, to send it through and to do parameter averaging or gradient averaging. This is actually a very common technique. The research has been showing that it's doing very well, and so I'm not sure exactly your experience, but I know that a significant amount of research has been done on this, and they're showing that that's a technique that's pretty well accepted in the industry. So yeah. Any other questions? Fantastic. Yeah. All right, anybody else have questions? No? Okay, well, thank you very much.
Okay.